Okay, so sorry this is so late. I didn't quite get finished grading all the free responses, and so I wanted to go ahead and get this published so at least you knew what the most common mistakes were in case you haven't been able to look over yours specifically. So on the latest free responses, starting off with Unit 2 free response B, most common mistakes. On 1A, you had more than one tension force, and so you can't just label them both capital T. Suggestions would be T1 and T2, or TP for like the pendulum tension, and TW for the string attached to the wall. Again, it doesn't matter what you do, just make sure you do something that can distinguish between those. On 2A, a lot of us just completely left off the spring force on the 8 kilogram block. You put the tension force to the right from the string, but then forgot to account for the spring which is holding it in place. And that should have, a warning, should have gone off in your head that the block's sitting there, it's not accelerating, and so there should have been a balancing force to the left. So just be careful on things like that. Continuing on to a, somehow a lot of us, I mean not just one or two, a lot of us had the right spring constant but didn't show the correct stretch. For example, a lot of you said Fs equals Kx, and then you put in 40 equals K times 0.25, and then somehow K equals 800. No, by that math, you don't get that answer, right? So make sure that your work is supporting what you're saying it's supposed to be. The correct stretch was 0.05 because the original length was 0.20 and it stretched to 0.25. So remember that x in that equation is how much it changes. It's the stretch. 3a, they asked for it in terms of g, and so you couldn't put it as 3.9 meters per second squared. You had to write it 0.39 times g, which is the same quantity, but they wanted it in terms of g on Earth. So again, make sure you're reading and answering the way they've asked it. 3D, a lot of us used normal and mg cancel as justification for why the net force was 0, but that's only half the story, right? That's only vertically. What about horizontally? You could have then gone ahead and said that the horizontal force is canceled, but the reason you know that, and the easiest, best justification is the simplest. It said constant velocity. And if it says constant velocity, then acceleration is 0, and if acceleration is 0, the net force has to be 0. End of story. 4a, this was really suspicious, guys. I mean, I'm not saying that you just Google the answer, but a lot of you had a free body diagram that looked like that. I've never drawn a force landing on an object in any free body diagram I've ever drawn for you, and so it was really suspect that lots of us drew it looking like that, and that wouldn't get full credit. Always start the force on the object and move away from it. 3 free response B, the one you turned in yesterday, I think it was. Never, ever, 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 ever label centripetal force on a free body diagram. The net forces are the sum of all the forces acting, and centripetal force is a net force. It's ma, but a specific time of a centripetal acceleration. So ask yourself before you put a force on a free body diagram, hey self, who's doing the pushing or pulling? And if you can't answer that, you don't draw it. That is a reminder for momentum too, right? Just because something's moving to the right, if you can't say something's pushing or pulling it to the right, there's not a force. And so you have to be able to name it and label it appropriately. 4B and C, tension is smart. As you speed up in this scenario, the tension will go up, and as you slow down, the tension will go down. And so we had to think a little bit conceptually that 4B, what was happening was the tension is going to get smaller and smaller as we slow down, and they want to know when tension goes to 0, because after that, then it's going to fall out of the circle because mg is going to pull it in a smaller circle. And so you're setting a limit. You're finding when t gets to 0. What was the first speed that t gets to 0? And then 4c was the opposite, right? You were going to increase the tension until it breaks, and so we were finding the speed that would exceed t max. And then remember, this should be your three-step process for every single Newton second law problem. Draw the free body diagram including designating the positive direction of the x and y axes, keeping in mind my rule number 1, if there's an acceleration, make it along an axis and positive if possible. And then based on that free body diagram, write your FNet statement. It's literally listing positive and negative forces that are in your free body diagram in an FNet statement, and then substitute MA for the FNet. And that MA can either be translational MA, delta V over T kind of stuff, or it can be centripetal, V squared over R. But either way, those are MAs that get substituted for the FNet, and then you solve for whatever we're looking for. All right, and then finally, for B and C, you have to be careful with variables. They specified that they wanted you to express the answer in terms of the given quantities, and they gave you radius as capital R and mass as capital M, so you couldn't just leave it as generic little m and little r. It's almost like you need to read the question and answer the question they asked, not the question you were hoping they would ask or anticipating they would ask. All right, so that was again just some quick reminders. Keep calm, keep moving. If you don't know something, make it up and keep going. But you got this, so good luck and do well.